Hello everyone. Today we will talk about the fundamental understanding of GIS-based route optimization. In this topic, we focus on building a fundamental understanding of GIS-based route optimization. The main goal is to explain how routing problems are defined and analyzed within a geographic information system and why spatial data plays a critical role in route calculations. Learners will become familiar with the core parameters that influence routing decisions, such as travel time, distance, vehicle type, and basic road characteristics. This topic also introduces the concept of GIS networks by explaining how roads are represented as connected elements, commonly referred to as nodes and edges, and how these structures enable route analysis. Rather than diving into advanced algorithms, this topic emphasizes conceptual clarity. It helps learners understand how routing costs and simple constraints shape route calculation outcomes in real-world scenarios. By the end of this topic, learners will have a solid conceptual foundation that prepares them for advanced routing methods and practical case studies presented in the following topics. Route optimization refers to the process of determining the most efficient path between one or more locations by using spatial data. The objective of route optimization is to minimize travel time, distance, or overall cost, depending on the specific needs of the routing scenario. Route optimization is needed because transportation and field operations often involve limited time, resources, and increasing operational complexity. By optimizing routes, organizations can reduce travel time, lower operational costs, and make more efficient use of vehicles and personnel. This also supports better planning and more informed decision-making, especially in scenarios that involve multiple locations, constraints, or changing conditions. In everyday life, route optimization is widely used in navigation applications to find the fastest or shortest route between 2 points. It is also commonly applied in workforce management to plan daily visit sequences for field staff. In logistics and urban services, route optimization helps organize delivery routes, improve service efficiency, and reduce unnecessary travel. At the core of route optimization lies a simple question: how can we travel from point A to point B in the most efficient way? This question represents the foundation of all routing problems, regardless of their complexity or scale. In its simplest form, the A to B routing scenario involves a single starting point and a single destination, with no intermediate stops and no complex constraints. The objective in this basic scenario is usually to find either the shortest route in terms of distance or the fastest route in terms of travel time. However, real-world routing problems quickly become more complex. Routes must be calculated over road networks that include intersections, varying road characteristics, and different travel conditions. This is where GIS-based routing becomes essential. Geographic information systems allow roads and intersections to be modeled as connected networks and enable routing decisions to be made using spatial data, forming the basis for more advanced routing analyses. Maps and routing serve different purposes. While maps are used to visualize locations, roads, and geographic features, routing focuses on analyzing how movement occurs between locations. Routing requires more than a visual representation. It requires analytical models that can calculate optimal paths based on specific criteria. Spatial data plays a critical role in routing because it represents not only the geometry of roads and intersections but also the attributes that influence movement. Factors such as speed limits, road direction, and access restrictions directly affect how routes are calculated. Without spatial data, it would not be possible to evaluate these parameters accurately. Geographic information systems are essential for routing because they are designed to model road networks as connected systems. GIS combines spatial geometry with attribute information and enables complex routing analyses to be performed efficiently. This makes GIS a fundamental technology for data-driven routing and optimization in real-world applications. Route optimization is influenced by several key parameters that determine how routes are calculated and evaluated. One of the most important parameters is time, which represents the duration required to travel between locations. Travel time is affected by factors such as speed limits, traffic conditions, and the physical characteristics of roads. Distance is another fundamental parameter in route optimization. It refers to the physical length of a route and is often used when the objective is to minimize the total number of kilometers traveled, such as in fuel-saving or cost reduction scenarios. Vehicle type also plays a critical role in routing decisions. Different vehicles, such as cars, trucks, or pedestrians, may follow different routing rules due to legal restrictions, road accessibility, or safety considerations. As a result, the same route may not be suitable for all vehicle types. Waiting times represent delays that occur during travel, such as time spent at intersections, traffic signals, or service locations. These delays directly affect total travel time and must be considered in realistic routing scenarios. Finally, road characteristics, including road classification, environment, and access limitations, shape how routes are selected. Together, these parameters form the foundation of GIS-based route optimization and influence all routing outcomes. In GIS, a network refers to a connected system that represents how movement occurs between locations. In routing applications, road networks are modeled as a collection of connected elements that allow travel from one point to another. Routing requires a network because movement is only possible where connectivity exists. Without a defined network structure, it would not be possible to determine whether two locations are connected or to calculate a path between them. The network defines where movement is allowed and how different locations are linked. All routing calculations in GIS are performed on network structures. The way a network is built directly influences routing results by defining possible paths, connections, and travel behavior. For this reason, understanding the network concept is a fundamental step in GIS-based route optimization. In a GIS network, movement is modeled using two basic components: nodes and edges. Nodes represent points of connection within the network. These are typically intersections, junctions, or endpoints where roads meet or where routing decisions are made. Edges represent the road segments that connect nodes to each other. They define the paths along which movement occurs and carry important information used in routing, such as distance, travel time, and accessibility. In routing analysis, routes are calculated by moving along edges and passing through nodes. Nodes determine where direction changes, turns, or routing decisions take place, while edges define the available paths between these points. Together, nodes and edges form the structural foundation of all GIS-based routing calculations. Connectivity describes how nodes and edges are linked within a GIS network. It defines whether movement between different locations is possible and how that movement can occur across the network. Without proper connectivity, routing calculations cannot produce valid results. Movement in a network always follows connected edges. A route can only be calculated if there is a continuous path of connected road segments between the origin and the destination. If parts of the network are disconnected, those areas cannot be reached through routing. Connectivity is critical for accurate routing outcomes. Errors in connectivity, such as missing links or incorrectly connected roads, can result in unrealistic or impossible routes. For this reason, ensuring correct network connectivity is a fundamental requirement for reliable GIS-based route optimization. In routing analysis, a cost represents the value used to evaluate and compare different route options. Routing costs define how routes are measured and determine which route is considered the most optimal based on the selected criteria. The most common types of routing costs are distance-based costs and time-based costs. Distance-based cost measures the physical length of a route, while time-based cost represents the travel duration required to move along a route. Each cost type serves different operational objectives. Routing algorithms select routes by minimizing the chosen cost. Depending on whether distance or time is used as the primary cost, the resulting optimal route may differ. Understanding routing costs is essential for interpreting routing results and selecting appropriate optimization strategies. Time cost and distance cost represent two fundamental ways of evaluating routes in GIS-based routing. Time cost measures how long it takes to travel along a route and is influenced by factors such as speed limits, traffic conditions, and delays at intersections or signals. Distance cost, on the other hand, measures the physical length of a route. It focuses solely on how far a route extends and does not directly account for travel speed or traffic conditions. This type of cost is often used when minimizing fuel consumption or total distance traveled is a priority. Choosing the right cost depends on the routing objective. When the goal is to arrive as quickly as possible, the fastest route based on time cost is preferred. When the goal is to minimize travel distance, the shortest route based on distance cost is more appropriate. Understanding the difference between these cost types is essential for selecting effective routing strategies. The term, shortest path, refers to the route that has the lowest total cost between two locations. In GIS-based routing, this cost does not always represent physical distance, it can also represent travel time or another defined routing cost. In most routing scenarios, there are multiple possible paths between an origin and a destination. Each of these paths is evaluated by calculating its total cost based on the selected criteria. The routing system then compares these costs and identifies the path with the lowest overall value as the optimal route. Shortest path logic is fundamental to all routing analysis. It forms the core principle behind navigation systems, logistics planning, and workforce routing. Understanding this basic logic helps learners interpret routing results and provides a foundation for more advanced routing methods introduced in later topics. Road characteristics play an important role in determining how routes are calculated in GIS-based routing. One of the key characteristics is speed limits, which define the maximum allowable speed on a road segment and directly influence travel time estimates. Road type is another important factor. Highways, main roads, and local streets are designed for different purposes and support different travel behaviors. Routing systems consider these differences when selecting optimal routes, especially when balancing speed and accessibility. There is also a distinction between urban and rural roads. Urban roads typically involve lower speeds, frequent intersections, and potential delays, while rural roads may allow faster and more continuous travel. Understanding these road characteristics helps explain why certain routes are preferred over others in different environments. Routing constraints are conditions that limit or influence how routes are selected during routing analysis. These constraints are used to ensure that calculated routes reflect real-world rules and practical limitations. Common routing constraints include restricted or prohibited roads, such as areas that vehicles are not allowed to enter, as well as temporary road closures caused by construction or events. Waiting times at intersections, traffic signals, or service locations are also considered basic constraints that affect total travel time. Constraints play a critical role in producing realistic routing results. Without them, routing systems might generate routes that are technically short but impractical, unsafe, or illegal. By incorporating basic constraints, GIS-based routing provides more accurate and reliable route calculations. A vehicle profile defines how a specific type of vehicle behaves within a road network. It determines which roads can be used, which restrictions apply, and how routing calculations should be performed for that vehicle type. Different vehicle types, such as cars, trucks, and pedestrians, have different routing requirements. For example, trucks may be restricted from certain roads due to height, weight, or hazardous material regulations, while pedestrians can access paths that vehicles cannot. Vehicle profiles are essential for producing realistic routing results. The same route may be optimal for a car but unsuitable or even illegal for a truck. By applying appropriate vehicle profiles, GIS-based routing ensures that calculated routes align with real-world transportation rules and conditions. Data quality is a critical factor in GIS-based routing because routing results are entirely dependent on the accuracy of the underlying spatial data. If the input data is incorrect or incomplete, the calculated routes will also be unreliable. Common data quality issues include missing road segments, incorrect road attributes, and outdated information such as speed limits or access restrictions. Incomplete network connectivity can also prevent routes from being calculated correctly or lead to unrealistic routing results. Poor data quality can cause incorrect travel time estimates, invalid routes, or unreachable destinations. For this reason, maintaining high-quality and up-to-date spatial data is essential for producing reliable and meaningful routing analyses. Routing data is not static. Road networks and travel conditions change continuously due to infrastructure updates, construction activities, and evolving traffic patterns. These changes directly affect how routes should be calculated. Examples of real-world dynamics include newly opened or closed roads, temporary restrictions caused by construction or events, and fluctuations in traffic conditions throughout the day. If routing systems do not account for these changes, calculated routes may become inaccurate or impractical. Keeping routing data up to date is essential for producing reliable routing results. Updated data allows routing systems to reflect real-world conditions more accurately and supports better travel time estimation and decision-making in operational scenarios. Routing problems often start with simple scenarios involving a single origin and a single destination. In these cases, routing decisions are based on a limited number of parameters, such as time or distance, and involve minimal constraints. As routing scenarios become more complex, additional elements are introduced. These may include multiple destinations, various constraints, and different optimization objectives. Each added factor increases the complexity of the routing problem and requires more advanced analysis. Understanding simple routing concepts provides the foundation for addressing more complex routing challenges. This progression prepares learners for advanced routing methods and real-world optimization scenarios, which are explored in the next topics of this module. GIS-based route optimization is widely used across many application areas. One of the most common use cases is navigation, where routing systems help users find the fastest or shortest route between locations and support everyday travel decisions. In field operations, route optimization is used to plan visit routes for field staff, such as technicians or inspectors. Optimized routes improve scheduling, reduce travel time, and increase operational efficiency. Route optimization is also essential in logistics and urban services. It supports the organization of delivery and service routes, helps reduce unnecessary travel, and lowers operational costs. These use cases demonstrate how GIS-based routing concepts are applied in real-world scenarios across different sectors. In this topic, we covered the fundamental concepts of GIS-based route optimization. Route optimization focuses on identifying the most efficient path between locations by minimizing costs such as time or distance, and GIS provides the essential framework for performing this analysis. We introduced key elements such as networks, nodes, and edges, which form the structural foundation of routing systems. We also discussed routing costs and basic constraints, which directly influence how routes are calculated and evaluated. Together, these concepts establish a strong conceptual base. Understanding these fundamentals prepares learners to better interpret routing results and supports a smooth transition to more advanced routing methods in real-world optimization scenarios. This topic provides the foundational knowledge required for the rest of the route optimization services module. The concepts introduced here, such as routing parameters, network structures, and basic routing logic, are essential for understanding more advanced routing techniques. In the next topics, these fundamentals will be expanded through advanced routing services, multi-objective optimization approaches, and practical case studies. By building on this foundation, learners will be able to explore more complex routing scenarios and apply GIS-based routing concepts to real-world problems.